Thank you for joining our first session in our Education and Healthcare web series. This session is titled Let Eaton Help You Pay Your Electric Bill, Power Factor Correction, and is presented by Dan Carnevale. Dan received his bachelor's degree in electrical engineering from Gannon University and his master's degree from Rensselaer Polytechnic Institute. Dan has over 15 years experience in power system analysis and is a registered professional engineer in Pennsylvania, California, and Alaska. All parties will be in a listen-only mode until the question and answer session of today's call. Also, the call is being recorded. If anyone has any objections, they may disconnect. At this time, I will turn the presentation over to Dan. Sir, you may begin.
Thank you, and my name again is Dan Carnevale. As the operator mentioned, we will be recording this session, and this session will be posted on our website following about a 2-week period. We will have a period for questions and answers at the end of the session, so please, if you could, write down the slide number that you have a question on and record that, and we'll answer the question after about a 45-minute presentation part here. It's interesting, I spend most of my time discussing power quality issues, and selling power quality or talking about power quality is a lot like selling insurance or talking about insurance. And what happens is people discuss power quality issues like transients and harmonics and surges and things like that, and they become, confused because it's like, well, I could have a problem later, I might have a problem later, but I get kind of passionate about talking about power factor correction, and the reason is because it's real money that people are spending every month on their utility bill, and when we discuss power factor issues with customers, they become excited because they realize that they're paying this money every month and they see a real ROI at the end of the month, and they see that there's dollars available to pay for the solution. But when we talk about power factor, I'm often met with one of two responses, and that is, one would be, oh, power factor, we've done that, we've been there, done that 10, 20 years ago. We've taken care of that problem. And the other response would be, what is power factor? What do I need to worry about? I've never heard of that. Is it really on my bill? And for both of those cases, I would challenge you to think that for the first case, that there may be, because of deregulation or new loads in your system, there may be a reason why you need to reconsider power factor. And for the second case, hopefully we can educate you today on some of the issues that are involved with power factor, and hopefully tell you some of the reasons why you should be concerned to look a little deeper into your bills, or maybe if you haven't considered or looked into your bills, maybe you should take a look at them and maybe you'll uncover some hidden charges there, and that's why we're here today. So we're going to try on this next slide just to do a quick poll just to see if anybody has currently had installed power factor correction capacitors or harmonic filters which actually do power factor correction at your facility. And just want to try to do a poll. We'll do an online poll. It'll come up with the numbers, and then we'll do the response. So if you can see these check boxes, now we're about 50% response no and don't know. I guess you can all see that. Yeah. So that's good. I think what this is showing is that a lot of us either have not considered it, or maybe don't necessarily know whether or not we have a charge, or we don't necessarily have anything on our system right now. And that could be for many reasons. It may be that the utility company doesn't charge a penalty, or maybe we don't have we haven't considered it in the past. Okay. Now we've identified some learning objectives, and by the end of this session, we hope that we'll be able to you'll be able to actually discuss and talk about these things that we're going to define for you today. And the first one is really to define power factor. What is it? Secondly, we'd like to identify potential power factor charges on the electric bill, and that's a lot of times the most confusing part. So we're going to go through some examples. Thirdly, we'd like to identify solutions available to correct power factor. And then we'd like to explore other benefits of power factor correction. And there's some reasonable other benefits that aren't necessarily going to show an ROI directly, but we'll tell you what those are, and there are other reasons why you would install power factor correction. Additionally, we'd like to summarize how harmonics affect the application of power factor correction capacitors, because that's an important issue today. And then finally, and one of the main reasons we pulled everybody together today was, of course, to calculate the return on investment. for power factor correction. So when you look at your utility bill, where has all the money gone? You know, you look at the bill and it has many different charges on it. And those charges could include things like kilowatt hours or energy, demand charges like kilowatts or kVA demand. And sometimes they have power factor charges, and sometimes they have other things like taxes. Of course, Uncle Sam has to take his dollars out too. So we always have taxes. And that adds up to a total. So whether your bill is, $3,000 or $30,000 or $300,000 a month, all of these charges go into your bill. And every utility company has different rate structures, and we're going to talk about some of the different reasons today. But what we're here again to focus on are these power factor charges. And coincidentally, all of these charges are affected by power factor. In most cases, taxes, demand, and energy can possibly be reduced by applying power factor solutions. So what is power factor? Power factor is really a measure of the efficiency or the efficient use of working power versus the total power that's supplied by the utility company or by the generators that you may have on site. And so it's the power factor is the ratio of kilowatts versus kVA. kVA is the total or total power that's used. Poor power factor is really costly for the utility companies, and so they try to incentivize and get the customers to apply solutions close to their facility so they don't have to ship additional power all the way down through the system. And this is why they impose power factor penalties. kVA is a combination of real power, or the power that we say does the work. It moves the equipment, it provides heat, things like that, and reactive power, or kVAR. And kVAR, we typically say, is the magnetizing power. So it's the power that magnetizes the motor that allows it to spin. It's power that magnetizes the transformer that allows it to operate. Kilowatts, or the energy, has to come from a generating source. So that has to flow through the system, either from a utility or from a local generator. But capacitors and other power factor correction equipment can provide a source of kVAR locally so that you can provide that kVAR locally to the loads, and you don't need to supply that all the way back through the system. So if you can eliminate the kVAR part of kVA coming from the utility, you're simply left with kilowatts, which really means that ratio on the previous page is 1, and that you're using very efficiently using the power from the utility company. We're going to give you a couple examples here. First, as an example, we'll use a 100 kilowatt load with a 0.8 power factor, and this really means that the kVA used to supply the load is 125, or 100 divided by 0.8. If we wanted to correct the power factor from 0.8 to 0.97, we would actually apply, in this case, a 50 kVAR capacitor. And by doing that, we'd actually be able to reduce it from 125 kVA to down to 103 kVA, just to supply that same 100 kW load. So again, this 100 kW load, 100 kW has to come from a generating source. But again, the kVAR can come locally from some capacitor, for example. And that's a reduction of about 20%, so that can be significant. Now, a lot of people, like myself, we like to see things visually with a picture, so this shows that same example with a picture. For example, the motor on the left actually requires 125 kVA, or 100 kilowatts and 75 kVAR to operate. Now, that could totally come from the utility transformer just north of that, or it could come from, part of it could come from that capacitor just to the right of that. So 50 kVAR comes from the capacitor in this case to provide of the 75 kVAR, and then the additional 25 kVAR comes from the utility source. And you can see with the blue and the gray scale there that it's a significant reduction in kVA and also amps back through the system. So you can appreciate the actual kilowatts or kVAR savings, kVA savings, and actual amp savings. Why do we consider power factor correction? Well, the primary benefit really is to reduce the electric utility bills, and a typical payback may be less than about 2 years. Other benefits, though, we mentioned we're going to talk about other benefits. You can increase system capacity. For example, if you have double-ended substations, you can actually increase the system capacity to where you can provide all of the load off of one transformer. Another issue that's important to people is voltage regulation, and capacitors help to improve voltage regulation. Another reason is you can reduce the losses in transformers and cables. Remember how I said if you reduce the overall kVA back through the system, you also reduce the current. So you're actually reducing I squared R losses back up through the system. And then finally, you can reduce harmonics in the power system if you use harmonic filters as a means to correct the power factor. Now, we're here to discuss healthcare and education facilities, and so we wanted to point out a couple loads that might be important in these facilities that exhibit low power factor. And specifically, if you can think of any motors in your facility, those motors will typically have a little bit lower power factor. Things like HVAC, pumps, elevators, compressors. And then there's other things like electronic loads like computers and other UPSs and things like that often exhibit a low power factor, especially when they have a lot of harmonic current. This table is taken out of an IEEE source, and this source actually says, for example, for hospitals, a typical power factor that's uncorrected, meaning no capacitors are installed, might range from 75 to 80%. An office building might range from about 80 to 90%, and this would be an example of, for example, administration buildings, data centers, smaller outbuildings that might be on campus, for example. So these are typical numbers that you can expect to see in your facilities. Now, when you look at a bill, again, it can become very confusing. There's all kinds of numbers and things on the bill, and typically what we look at on our bills, and if you're like me at home, I look at the bottom line. What am I paying this month on my bill? On this bill, you can see, though, there's a lot of other things like kilowatt hours, kVAR hours, kilowatt demand, PFM, and adjusted demand. Now, what's PFM? I highlighted that in red for a reason. PFM on this particular bill really means power factor multiplier. And again, if you didn't read the footnote on the third page of the bill, you wouldn't know that PFM stands for power factor multiplier. It's going to be interesting. I think we'll show you on this example where the hidden charges are in one of the following examples. Now, have you ever analyzed your electric bill? Another polling question we'd like to ask. You can just check either yes, no, or someone else at my institution has. Okay. Sorry, I had to open the poll. Okay, right now we have about 33% yes, 42% yes, 42% no, and 14% someone else has. So about half and half, I would say, that have analyzed your bill and half haven't, and then a small percentage someone else has actually analyzed the bill. And so, does that show? That should show the results. Okay. Now again, part of that, part of the reason you don't necessarily look at the bill is because different parts of the company or the facility pay the bill versus actually would be the person to analyze the bill. And we want to talk about how do utility companies bill so that we can understand what's important on that bill. They always measure usage in kilowatt hours, for example, and that's what we're used to in our residence. We typically have charges that are something like 5 to 15 cents per kilowatt hours. For larger customers, like most of you, they charge a kilowatt or kVA demand, and that's typically a 15-minute average number. So, for example, if you're using 1,000 kilowatts for the past 15 minutes, that might be the most you used over the past month. They're going to charge you a 1,000 kilowatt demand charge as well. And that's a one time a month charge, and the charge is typically $5 to $15 per kilowatt or kVA, for example. Now, additionally, they may put power factor penalties, and they may be part of a demand charge, or they may be separate charge built into, for example, even the kilowatt-hour charges. And sometimes, again, the utility company will try to incentivize the customers to actually install power factor correction by giving a minimum threshold for power factor, and they'll say something like you need to have an 85% or 95% power factor maintained, otherwise we will charge a penalty. So how can you really justify putting in equipment? Well, if you know the actual amount of the penalty, so you know you pay $3,000 out of your $30,000 bill every month goes to the power factor penalty, and then you just go out and calculate the penalty. All you have to do is go to the website and take the tariff off the rate structure off the website, and then you just calculate the size and cost of the equipment. Sounds really easy, doesn't it? Actually, it's kind of interesting. You go out to those tariffs, and they're very confusing. They may be 150 pages long, and that's why we say, are there any lawyers in the audience? I think if you don't actually do this stuff every day, I'm often confused, and I've looked at hundreds of utility tariffs. I'm often confused the first time I look at the tariff schedules as to what the actual penalty may be, and if I've included or not included enough information to actually come up with a real number. How do you read these tariffs? Each utility company has rates that vary according to load type and size. So that means if you're a 1,000 kW customer, you pay a different rate than a typical 100 kW customer. And that's why in our residence we only pay, for example, kilowatt hour charges, and in larger facilities we pay kilowatt demand charges as well. Then you need to determine your rate schedule type. So again, there's a subset for every utility that is the schedule type, and that's really by size and type of load. I've even seen, for example, catfish farm, tariffs. So there's a whole lot of different tariffs out there. It really just depends on what you are as a customer, as how the utility applies your rates. Then you want to, a lot of times you can discuss the rate schedule with your utility account rep, and sometimes they'll be able to tell you whether or not you have a power factor penalty. Sometimes they won't, and out of no fault of their own necessarily, because things may have changed, or they may not be aware of some of the quote-unquote hidden charges that actually become power factor penalties. And there's too many variations really to make generalizations, but we'll give you a few examples. We're going to have 6 examples in the following pages. I'm going to quickly go through them just to show you the variety of different things that there are as far as ways that utilities charge power factor penalties. This first example is, again, taken right out of the tariff, and I think the most interesting thing on this one says, the customer on this schedule should maintain unity power factor, which means very efficient use of power. But they say anything below 95%, if the average power factor is less than 95% lagging, the billing demand charge will be increased by 1% for each percent or fraction thereof that the average power factor is less than 95%. And so, for example, if your demand was 1,000 kW and your actual power factor is 87% or 0.87, remember again, they say the demand has to be greater than 95, so it's less than that. So they're going to increase your demand, and they're going to adjust it by 95 minus 87, which is 8%. So they take that 1,000 and multiply by 8%. And so you're paying 1,080 kW even though you're only using 1,000 kW. So that really means that your penalty is 80 kW times the demand charge, or $10, or $800 a month, or $9,600 a year. And $9,600 a year is quite a bit of money to be able to spend on power factor correcting equipment, and you may be able to pay that off in 6 months, for example. Here's another example, and if you can read the, again, fine print, basically this one says that the kilowatt hour charges are going to be adjusted by a certain value if you actually have lower than, in this case, 85% power factor. And if you can see down below, they say, for example, on our example here, we use the power factor of 0.8, and we have 500,000 kilowatt hours usage during that month. We would say that for a 0.8, the multiplier is 1.15, or a 15% penalty. That's $90,000 a year that you're paying a penalty on a $500,000 or 500,000 kilowatt hour a month bill. The third example, and coincidentally, based on that one, you were only supposed to maintain 0.85 and you're only at 0.8, so it didn't seem like that was that big of a jump, but you're actually paying $90,000 a month, which I think is very significant. The next example is really, again, that power factor multiplier. That was the one I pointed out earlier. And if the power factor multiplier from this crazy equation comes up and it says that you're going to pay 1.25, that's again like a 25% penalty. So you're going to pay 250 kW more in this case than you would. So you're paying 1250 kW worth of demand rather than 1,000, which you're using, and that's $30,000 a year penalty. The next one is just an example to show you that for various load sizes, for example, 0 to 185%, you're required to maintain an 80%, and over 2,500 kW, you're required to have a 95% power factor. So obviously for larger customers, they don't want them to have lower power factor, or they're going to incentivize them to actually correct the problem. And this one, again, adjusts the demand based on what your actual power factor and your load is. This is a kind of interesting one, and I think that in many cases, again, this is one of the ones that you have to look a little more detailed at, because there's a cost and a benefit for applying power factor correction in this case. They say that they'll decrease your demand for every percent that the monthly average power factor exceeds 80%. So if you're above 80%, it's a benefit. If you're below 80%, it's a decrease an increase in your kilowatt demand, and they increase it by, for example, 0.6%. So for a customer that has a demand of 1,000 kW, there's not only a benefit to bring it up to 0.8, but there's also a benefit to bring it up beyond 0.8. And in this case, you could end up with about $13,212 a year for less than power factor 0.8, and the opportunity of greater than power factor of 0.8. And you're going to wonder why I got that $11,000 or $13,212, and I'll show you some of that later. Now, finally, this sixth example is probably one of the more detailed ones that is out there, and this one actually affects your kilowatts because you're actually being charged kVA demand, which really means anything less than 1.0 power factor is going to cause a power factor penalty. And also, if you see down below, they actually charge your kilowatt hours based on certain levels of kVA. And so your kilowatts are affected, your kVA are affected, and your demand and your kilowatt hours are affected. And as it turns out down below, you can see just for this 1 month that we show as an example, the demand penalty is $1,846, and most people would be able to calculate that based on the kVA versus the kilowatts. But the hidden charge in this case, I think, is really the kilowatt hour penalty, and that's almost as substantial, some cases even more. I could show you other examples. But for almost $3,000 a month, or more than $30,000 a year if you had a constant load, and again, you'd have to figure that all out based on the month of the year and everything else. But you could look at all these numbers and actually calculate these penalties. What I'm trying to show you again is that there are dollars out there available to be saved each and every month. In most cases, a lot of people don't even realize they're there. Now let me give you an example, and I tell you this is a real life example. It just happens to be from the building I'm standing in right now, and so nobody's immune to this hidden charge. We kind of looked at our bill when we built this building about 5 years ago, and it was in the winter, and we didn't think we had a penalty. Well, as it turned out, in the summer, power factor dropped to about 0.86, and that was below the actual level that the utility requires, which is 0.95. And you wouldn't even think that that's much of a substantial penalty, but it turned out that it was about $2,000 a month just on this bill. And the way it, again, is applied in this bill is we used 1,146 kW. There's a power factor multiplier of 1.14, so they adjusted our demand, our kilowatt demand, up to 1,307. And we paid 1,307 versus 1,146, or 161 kW more each month in this case just because we had a low power factor, and it wasn't even substantially low. Now, if you look at 6 months worth of data, and on the left-hand side are the dates going from July back through February, you can see that the penalty way over on the right side, where the potential savings is anywhere from $1,900 or $2,000 down to $315, or $7,200 or almost $7,300 in 6 months, or about $14,000 in a year. So where do all those charges come from? Well, you take that demand charge, which is now $13.07, for example, and you multiply that by the dollars per demand. In our case, we pay $12 per demand of total generation, transmission, distribution charges. This is more detail on that example, but it turns out that we applied a 300 kVAR fixed capacitor bank, and the return on investment was less than 5 months. Almost like a no-brainer, but we didn't realize the penalty was there. So, and again, the reason is because the people that pay the bill don't necessarily look at the bill or don't necessarily analyze the bill as we would. Now I'm going to introduce what we call the power factor correction tool, and it has several pages. It's an Excel spreadsheet tool that our sales engineers use. And this particular page of the tool actually calculates the potential penalty for various utility companies. So we have these set up for various utility companies around the country. And it's, again, to uncover some of these hidden charges. And so within typically 15 minutes, we can analyze someone's bills. And whether you have 1 month's worth of bill or 12 months, we can analyze roughly what the potential savings could be per year. Now, again, remember the steps I said were that you have to, first of all, figure out what the penalty is, and then you just select the equipment. Well, the next step is really to select the size and type of power factor correction, and that can be problematic as well because it can be somewhat confusing. But I will tell you that there are tools available to figure that out. You determine, first of all, the target power factor. So if the utility says you have to maintain a 0.95, then that's your target power factor. If they say that you're on kVA rates or your power factor should be unity, then that's your target power factor. Then you can typically easily determine with tables or software the size of power factor correction equipment required. And again, that's pretty readily available today. You select the type or the size to avoid the penalty, but secondly, and importantly in many cases, to minimize the negative effects like overvoltage, for example, or harmonic resonance, which we're going to talk about later, or losses through the system. Overvoltage is an important issue. If your load is on all day and then off at night, you may apply a capacitor and the voltage might go very high at night and you could have other problems. And then a final consideration is really to think about where you're going to install it, low voltage or medium voltage, and where you're going to apply it. Either, for example, at the motor or at a central location, which is more common. And typically you'd put it at the metering point with the utility just to avoid the penalty and not necessarily worry about other issues downstream. So what's the right answer? And as with a lot of things in the engineering world, it really depends. It depends on the application, the budget, the physical space, and really the preference of the customer. Now, what type of power factor correction equipment should be selected? Well, what's available? Well, capacitors are the easiest or most fundamental power factor correction solution. And then there's harmonic filters, which we typically call tuned or detuned. And then there's things like active harmonic filters or active filters, which actually are power electronic equipment, a lot like a variable frequency drive, if you're familiar with those, that provide power factor correction. And then you have to consider, really, again, low voltage or medium voltage, fixed or switched. What kind of power factor correction solution do I need to apply? What else should be included? And I like to tell people that if you only look at the cost of the capacitor or harmonic filter, then you're really missing the true return on investment. You really have to think about what's the breaker or fuse disconnect that I'm going to use to feed this thing. And then what's the installation cost? Is there labor involved, cable shutdown? These are very important to understand the total cost. If you leave these out, your return on investment may look a lot sooner than it really may be, and we don't want to try to fool anybody. So let's look at the actual solutions. Here's a low voltage fixed capacitor bank, and they're typically, either wall mounted or floor mounted, and they're in the 100 or 1 kVAR to 400 kVAR range, 208 volt through 600 volt typically. But you notice down here it says must be in a harmonic-free environment, and as we know, none of our facilities are a harmonic-free environment anymore. I mean, I think we have to deal with that all over. There may be situations where they're low harmonics, and we don't have to worry about it, but we'll consider why we need to worry about that in a couple minutes. Next, we have low voltage automatic or switched banks, and they could be, again, left is floor mounted for larger banks, or right is wall mounted for smaller banks. And these have a small controller in there that actually takes in and out steps of 50 kVAR, which actually controls the capacitors, or in this case capacitors, so that you don't cause that overvoltage issue, for example. And you can regulate around the actual power factor that's required. This section shows a low voltage harmonic filtering equipment, and again, this provides very similar power factor correction as a capacitor bank would, but it also avoids harmonic and capacitor interaction problems, and it may be used to filter out some harmonics that are bad on the system to reduce voltage distortion, for example. Then as you go to medium voltage capacitors, we're probably all familiar with driving down the road and seeing up on pole-mounted racks these capacitor banks, or you may see in a substation the rack-mounted capacitor banks, but mostly what we see for facilities like yours are going to be metal enclosed or pad-mounted capacitor banks, medium voltage. Medium voltage are typically the best value, meaning the lowest dollar per kVAR value, and they're in the range of 2.4 to 24, or even sometimes higher kV range. And sometimes you can pack as much as 20 megavar into some of these metal enclosed banks. We could, use parallel banks for larger systems, and they're typically, rugged switchgear enclosures. Here's an example of one where we point out the bottom actually are the capacitors. There's 6 capacitors across the bottom, 500 kVAR per can. For a 3-phase system that makes 1500 kVAR on the left and 1500 kVAR on the right, and then you have fuses on the top, inrush reactors in the back, and vacuum switches in the front. Now, we mentioned harmonics a few times, and what's the big deal with harmonics? Well, we have to consider harmonic resonance if we're going to apply power factor correction solutions, especially if we're just going to put power factor correction capacitors on the system. If you look here, the waveform on the left shows a nice sinusoidal waveform, and then all of a sudden it goes crazy. Well, what is that craziness? That is harmonic resonance. And if you look on the right, that's a failed capacitor from a medium voltage larger installation where it actually caused resonance, or the resonance caused failure. I'm going to explain resonance by first talking about mechanical resonance. Mechanical resonance is something that we typically see in our lives every day. For example, plucking a guitar string at a certain frequency, or a pipe organ that might resonate at a certain sound, or a stretched spring. But for many of us as engineers, a lot of us have probably seen that Tacoma Narrows Bridge video off the internet. If you haven't seen it, I'd say that you ought to go out and take a look at it. It's very interesting to see the video. It's from, I guess, the 1930s. This bridge was actually built, and then all of a sudden it started resonating because of the wind. And I'll show you the next few pictures. They're snapshots of the bridge as it's resonating. You can see the bridge is kind of turning left to right, and what they were saying was it was like galloping up and down as well. So it's going left, right, up, down, and then all of a sudden it failed. And it was pretty dramatic when it happened. It's again, very interesting. You should try to take a look at that video. You can see people in cars actually going across the bridge in the early part of the resonance where it was. People, I guess, didn't worry about the safety issues, but anyway, it's kind of very interesting. But as you look at that, without the wind, there would be no resonance in that bridge issues, because as every structure, electrical or mechanical, has a resonant point, if you don't excite that resonant point, you don't need to worry about it. But with harmonics and capacitors are typically a sink for harmonic currents in the system, but they also change the resonant frequency of the system, and that's why we're concerned when we put capacitors on. And if you put if the parallel resonant frequency when you put a capacitor on the system is close to a harmonic generated by a load like a drive or computer loads, for example, harmonic resonance can occur. And again, harmonics are like the wind in this example. They excite the resonance of the system. Capacitors that have been on a system for years may not have any problems until you add harmonic sources to the system, and that's why we're so concerned today. Electrical harmonic resonance, unfortunately, is said to be a self-correcting problem, and typically the way that you see it manifest itself is capacitor fuses will fail or open. Capacitor cans may actually fail, or other system equipment could fail. And there's an article that I put together in EC&M magazine, and we also posted on our website about power factor correction and harmonic resonance if you're interested and you want to look further into that. Again, as an example, if you have a 200 horsepower drive down on the bottom left and you have normal motors on the system, but you add a capacitor bank to that system, a 600 kVAR capacitor, you can use this formula and these equations, which are the subject of a whole nother webinar, to actually go through and analyze and figure out that the resonant point is close to one of the frequencies generated by that drive. In this case, it could be close to the 7th harmonic. And it could amplify the harmonics out of that drive. So for example, if the drive produced 10 amps of 7th harmonic current, you can amplify it to 600 amps flowing back and forth between the capacitor and that transformer. So again, that's why it's self-correcting. You can't have that situation for very long before something fails. Now, how do you solve that problem? Well, there's really two methods. One is you change the method of kVAR compensation by applying, for example, a harmonic filter or an active filter instead of a straight capacitor. Or you can change the physical size or the electrical size of the capacitor bank to overcompensate or undercompensate for the required kVAR. But you have to live with the ramifications. For example, you may have additional overvoltage if you put too big of a capacitor on, or you may still have a power factor penalty if you don't put big enough capacitor on. So you may eliminate most of your penalty, and you may not eliminate all of it if you put a smaller capacitor on. Now, the bottom left-hand picture shows harmonic resonance near the 13th harmonic, which really, if you look, the waveform that's in the background is a superimposed 13th harmonic on top of a 60 hertz. On the right, what we show are the red lines vertically show the harmonic resonances or the harmonic sources that are available in the system, like 5th, 7th, 11th, 13th, for example, and it's showing different sizes of capacitor banks. So as you approach one of those red lines, you could have an issue. Now again, sizing the capacitor bank is very important as far as, or capacitor bank or other power factor correction solution is important to this whole process, because you need to come up with the right size, not too big, not too small, and also avoid resonance issues. And this power factor correction tool has another page that we use to actually put in system data and sort of do a small model of the system to both look at what size capacitor bank or harmonic filter, for example, should be used, and really what is the target power factor so we can apply the right solution. This also looks at harmonic resonance points with a given transformer size and impedance so that we can understand what we need to avoid. At the bottom of that same page, typically we will give the estimated installed cost, and again that will include a breaker or a cable, cabling installation costs, which are very important to understand again. So once you know the cost, the total cost, and you know the actual penalty per year, you can take those two and provide a simple ROI, or return on investment. So down below you can see that for the 5 prices given, or $5 values given, and the one in blue at the bottom is the actual installed cost. So we estimate the numbers, and then we give an actual block so that if somebody knows what the total is going to be, they can put it in. Again, this is how we come up with a 5-month payback at our facility. Now here's another example that might be, again, more appropriate to one of you. This particular customer, large university, had about $200,000 a month bill, and of that bill, they paid about a 10% penalty for power factor. If you look at the numbers, they were paying on kVA rates, and they were about 10,500 kVA with 7,700 kW, power factor 0.73. So again, they were supposed to maintain a unity power factor 1.0, and so they were paying about $240,000 a year penalty. and the payback for installing some low and medium voltage solution was about less than 18 months. So again, it was a pretty good return on investment for them, which even more interesting is that you're paying that $20,000 a month, in this case, penalty. So they actually have considered a leasing option. And so if you're paying $20,000 a month and you lease it for, say, 3 years, you can actually pay $15,000 a month on the lease and get $5,000 a month positive cash flow in your pocket. So there's ways to use the money that's already available that you're paying on your bill anyway. Now again, we tried to summarize some things for you within this session, and we hope that we've covered with this web session, defining power factor, identifying some potential power factor charges on your bill, identifying solutions that are available to correct power factor, and looking at some of the other benefits of power factor correction. We hope that we've at least initially introduced you to the concept of harmonics and what you need to be concerned with. And then finally, we hope that you're able to calculate and look at the return on investment for power factor correction equipment. Now, what should you really do? Well, our suggestion would be that you should take about 12 months worth of utility bills, and as we learned in our own facility, the winter and summer months may be dramatically different. So it's important to look at 12 months. You should examine the bills and look for obvious indications, as we just pointed out, things like power factor multiplier, KVA rates, kVAR charges, kVAR demand charges, things like that. Adjusted demand, things that don't necessarily jump out at, say, power factor penalty. A third step might be to actually call your account rep and ask if you pay a penalty. And they may say yes, and if they do, then you should really consider, well, what am I paying per year? And if they say no, it may mean that you don't pay a penalty, but it also may mean that you do pay a penalty, and they either don't know, and the rates may have changed, or they don't actually associate things like KVA rates with poor power factor. The next step would then be to size the corrective equipment using tables or tools that we showed that are some available. And again, power factor correction equipment manufacturers will have the tables and tools available to do that. And then you calculate the return on investment. And most people, I find, accept less than about a 2-year payback. And coincidentally, most of the applications that I've looked at are well less than 3 years, and most are less than 2 years. A lot are less than 1 year, so it's very, very appropriate to apply this equipment. So we'd like to thank you, and at this point, we'd like to ask the operator to go ahead and open the line to have additional calls come in with questions. And for further information, we'll show, so if you have a question, press star and then the number 1, and then the operator will connect you with us to ask the question. And for additional information on power factor correction, we have a power quality hotline or support line, and that number is shown here, as well as we have some technical papers on all of these subjects on our website. And if you just use the power factor or harmonics search in the keyword, you'll find this. Again, we will have a recorded session of this if we don't, or within 2 weeks on the website. One of the questions that we had come in through the website was, have you seen changes in the way utilities bill for power factor? And I would answer that in a couple ways, I guess. With deregulation, utility companies don't necessarily, I guess, provide the equipment as easily for their customers, let's say. Or you remember in the one rate schedule it said the customer should actually maintain a certain power factor. Well, there are a lot of power factor penalty clauses built into rate structures, but if you look at your bill, you may find that you don't even pay the penalty. Well, it was built into the bill, but it was never enforced. And I found that if you look at your bill and you don't see it on there, or you do see it on there now, your rep may not even know it. And again, that's one of those things that may be a hidden charge or may be unavailable to see. But let's see, one other question. Oh, based on Eaton's experience, are there any portions of the country that are more affected by power factor charges? Basically, what we've seen is there are definitely areas of the country where utility. What I found was an old Westinghouse document. It's kind of interesting. And back in 1979, they put together a list of all the utility companies around the U.S. And they said, for each utility company in, say, for example, Pennsylvania, they listed how the power factor penalty may be applied and what type of power factor penalty it might be. Does it adjust the demand? Does it adjust the kilowatt hours, for example? And I found that there are some very significant penalties in areas like, for example, Philadelphia. They adjust both the demand by having KVA rates in some cases and also the kilowatt hours to the extent that you're paying about $25 per KVA or kVAR demand that you have on your system, but total additional penalty. So it's pretty substantial around the country. Is the operator Mia?
Yes, we do have one question from the audio portion.
Okay.
Jack Hawkins, go ahead.
Hey, Dan. In the Northeast, specifically the Connecticut area, Northeast Utilities has a rebate program for correcting power factor to 0.816, and they have to have a study done. And there are a lot of people that go out and do studies. Obviously, Eaton can do power factor studies and look at the harmonics on a system. But these other folks are coming in and slapping a meter onto a system for an hour and taking readings and then coming up with the capacitors that they feel are required. And basically what's happened, of course, is Northeast Utilities has gone from kilowatt hour pricing to demand pricing, okay, because their system is so overtaxed.
Right.
Originally it was in the Southwest corridor. It's all over the state now.
Right.
I guess, and they look at harmonics. My question is, how does somebody that puts a meter on something for an hour,
how do you figure out? Yeah,
really determine what's going on? Because you're talking about harmonics and the variance of those and different loads that are on at different times, and the basic loads that a plant carries. And again, does it operate 24/7 or is it a 5-day operation? What happens when you shut loads off over a weekend and you get over voltages?
Mm-hmm. Well, I mean, those are all good points. I mean, I think the part that we kind of went through quickly, again, to show that, there's a lot of variations on the size and type of power factor correction equipment is that you can put in fixed and switch. Now, why do you put in switch? Just for those examples, Jack, of if your load is not 24/7, if it's, like this office building here, we would typically have very light load on the weekend to the extent of maybe a third of the normal load. And that would be why you put a switch capacitor in. So if you go out and measure for an hour, what's the chances of that hour being either the heaviest or the lightest or somewhere in between load? And really, are you going to correct the power factor based on the utility bills or just that measurement? I typically like to say that you do a combination. First of all, we do the screening with the bills just to see if you're even paying a penalty typically. And then as you actually apply the solution, you really have to look into more detail, as you mentioned, Jack, and that is really to look at whether or not you need fixed or switched. And as you look at that, if you do an hour's worth of measurements, you may see some harmonics, you may not. If you don't see harmonics, it doesn't mean they don't exist on the system. It just may mean that the loads weren't on at that point.
Right.
So if you're going to look at applying, say, for example, a straight capacitor, you may need to adjust that capacitor. And what I suggest to people is that you never apply a capacitor with a known dangerous resonant point anyway. At this point, I mean, that would be on a system where you could potentially add, harmonic sources later, which means that you don't put a capacitor that's going to cause parallel resonance near the 5th or 7th or 11th or 13th harmonics, because those are going to be the prevalent harmonics on a typical 480 or 600 volt system. that we see today, and that's going to be the ones that are going to excite residents and cause potential issues later on.
Okay. I just see this, and I see the difference between, like your building, between winter and summer and what's going on. And I just watch what some of these guys are doing, and I to the customer, protecting a customer who's buying a capacitor, these guys have to be putting in switched banks that they may not need all that capacitance. They may be way overpaying for what they really need. I guess that's part of my point.
Right, and that's exactly the point is, what do you really need, and what exactly are you looking to do? So if you're trying to solve just the utility billing problem, then, like we put a fixed bank in this building, and I'll tell you, it goes a little bit leading, but the utility company doesn't bill us for leading. And it goes on the weekends, maybe 0.98 leading, but the overvoltage is what I calculated was not substantial. So we looked at the negative sides and we looked at the positive side. And we want to have a 5-month payback, or do we want to have a 10-month payback? Well, obviously, a lot of people want to have a 5-month payback, but a 10-month payback wouldn't have been so bad if we had to. So you look at both and you say, well, what's my best choice for actually, I guess, applying. There's always the optimal or best solution, as far as best engineering solution, but there's also the optimal cost solution, and a lot of times you end up somewhere in between.
Right. Okay. Thank you.
Sure.
Again, if you'd like to ask a question, please press star and 1 on your touch-tone phone.
We did have a couple more come in through the website. The first one was, what is PFM? PFM is power factor multiplier. And that a lot of companies use that, utility companies use that as a method of adjusting your demand. So, like, for example, if your demand was 1,000 kW and they say the PFM is 1.15, they multiply 1.15 times your 1,000 and you get 1,150 kW that you pay a demand charge on. The way that the PFM is calculated is typically based on some power factor minimum requirement, and there's usually a very complicated equation that goes along with it, but that's what it means. Another question came in, are the presentations available to download? And that would be, again, in 2 weeks or say a little bit less, we're going to post the sessions on the website, and that will be the full audio and visual part of it. And that'll be our website, eatonelectrical.com, under the healthcare and education section of our website. Yeah, and if there's a couple other questions that we got that are a little bit longer on the website, we can answer those via email as we leave the session. I think we're coming close to the end of our session. Were there any other audio questions?
No questions.
Okay. Let's see if any of these are short enough we can answer. Is there a typical rate schedule for a hospital? And I would say no. There isn't, because every utility company is a little bit different. Again, it's based on your size of your kilowatt demand, or your bill each month, and basically, there's no such thing as typical across all the utility companies. But the thing that I mentioned earlier, which is interesting, I think, is that database that I found from 1979 from the old Westinghouse thing is that a lot of the rate structures are still similar, except for companies that have either gone under or changed by deregulation. But the structures are similar, but the rates are obviously different based on the years. So again, we'd like to thank you and let you know that we are here to help. We do have the tools available to help you run through these numbers pretty quickly. At least do a first screening screening look at whether or not you pay a penalty, which is kind of interesting in itself. And then really the solution oftentimes is up to you as far as, again, like in that one university example, if you're paying $20,000 a month already, there's lots of ways to do that, to skin that cat as far as actually, applying a solution, whether you put in a $15,000 a month solution and save $5,000 the first month, or whether you pay $150,000 and get a payback of 6 or 8 months or whatever you want. So we really appreciate you being on the call, and look forward to hearing from any of you if you have any questions in the future. Thank you.